the normal approximation for the binomial distribution. Today we're going to look at using the normal distribution to solve binomial distribution problems. So we know that the mean and standard deviation of a binomial random variable is as follows. Okay, we denote a binomial distribution by a capital B with n and p in parentheses. That means that the distribution is a binomial with n trials and p the probability of success. And we know from our study of binomial random variables that the mean of a random variable that's binomial is n times p. And we know that the standard deviation of random variable x, which is a binomial, is n times p times 1 minus p, and then we take the square root of that. And we've been studying situations like this, where let's say a basketball player is traditionally a 72% free throw shooter. In a season, she takes 427 foul shots. How many free throws would you expect her to make? And then B, calculate the standard deviation for the above problem. So x is the number of free throws made, and x is a binomial distribution with n as 427, and p, the probability of success, is 72%. So the expected value would be n times p, or 427 times 72%, which is 307.4. So that is the expected number of free throws that this player would make. And remember, we also call that the mean. And then for the standard deviation, we would take the square root of n times p times 1 minus p. So that would be the square root of 427 times 72% times 1 minus 72%, which would be 28%. By multiplying those together and taking the square root, we get a standard deviation of 9.28. Okay, so that is just a quick review of using the binomial mean and standard deviation formulas. What we're learning about today is the normal approximation for binomial distributions. Okay, what this means is this: as the number of trials of n gets larger, the binomial distribution of x gets closer to a normal distribution. Okay. So that means we start with a binomial distribution with n trials and p successes. P is the probability of success. And we can, at some point when n gets large enough, the binomial distribution becomes really close to a normal distribution with a mean of n times p and a standard deviation of the square root of n times p times 1 minus p. Okay, so we can use those binomial mean and standard deviation formulas in a normal distribution. So then we could draw a bell-shaped curve. We'd put n times p as the mean and the square root of n times p times 1 minus p as the standard deviation. And then we could use normal distribution to find the probability of certain events happening, like we have in the past. Okay. So it's a way to do a binomial problem using a normal distribution, which is pretty cool. Now, we can use a binomial, a normal distribution to approximate a binomial anytime we want, but it's not always going to be super accurate, okay? It gets accurate when a couple conditions are met, okay? So we would recommend using the normal approximation only when these two conditions are met. And that is that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Okay? Now if you think about it, this is the expected value of the successes. Okay? So as long as we're guaranteed 10 or more successes in our trials, and this is the expected value of the failures, because it's n times 1 minus p. Okay, so as long as we can expect 10 successes and 10 failures in our trials, then we can use the normal approximation to do a binomial problem, and our answers will be very similar, okay, to what they would have been if we treated it as a binomial. So this allows us to make sure n is large enough to assume our binomial distribution closely resembles our normal distribution. Okay, so as we move forward in statistics, we're going to be using conditions a lot. where there'll be things that we want to do, formulas we want to use, techniques that we want to use. But in order to make sure it's okay that we use them, we have to check that the conditions are met, or that the proper conditions are present in order to use those techniques. Okay, so this is our first look at conditions, and these first two actually will show up later on in the course as well. So this is our introduction to that idea. So as long as these two conditions are met, it is okay to use a normal distribution to solve a binomial problem. Here's an example. Suppose that 60% of adults have credit card debt. Okay, that's probably low. But if we surveyed 2,500 adults, what is the probability that more than 1,520 would have credit card debt? Okay, so I'd like to use a binomial, to solve this binomial problem. Okay, but to do that, I'd have to make sure that the sample is large enough to use a normal approximation. So I'd have to check, is n times p greater than or equal to 10? And is n times 1 minus p greater than or equal to 10? So for this problem, I would take 2,500 times 60%, because 2,500 is my n, 60% is my p, and that is 1,500. So that's at least 10 for sure. And then I would also do 2,500 times 40%. Okay. And that would be 1,000. And if I've done these correctly, the expected value of both should add up to my total sample size, and it does. And they're both at least 10, so that means I am okay to use a normal distribution to solve this problem. And remember, when we're talking about a normal distribution to solve a problem, it means that I can use a z-score. Okay, so that's where we're headed. To use a normal distribution. So let's try to answer this question. Since I know I can use a normal distribution, I can find the mean. Remember, the mean in these is n times p, which we already figured out was 2,500 times 60%, which is 1,500. So we would expect 1,500 people with credit card debt. And the standard deviation would be the square root of 2,500 times the probability of success times the probability of failure, and then I take the square root of that. And you can do that in one command on your calculator. And I get 24.5 roughly. We'll round to 0.5. Okay. So I have a mean of 1,500 and a standard deviation of 24.5. Now my question was, what's the probability that more than 1,520 would have credit card debt? So here's 1,520, and more than is over here. So now I can use a z-score. So I would say z is 1,520 minus 1,500 over 24.5. And I get a z-score of 0.82. Remember, we can round z-scores to 2 decimal places. And now I'm going to use the normal CDF command. And I'll use 0.82. And then remember, off the graph to the right, we use a 10. That gets me an answer of approximately 21%. So there's a 21% chance that in a sample of 2,500, I'd end up with 1,520 people or more with credit card debt. Okay, so we just did this binomial problem using a normal distribution. And we could do that because of those two conditions were met, that n times p is bigger than or equal to 10, and n times 1 minus p is bigger than or equal to 10. So don't forget, if we want to do a situation, a problem like this, we need to check those conditions. All right, good luck with the normal approximation to the binomial distribution.